Hello, everyone. Welcome to our Deep Dive podcast, where we review and discuss the latest and greatest in AI research. Today, we're exploring the paper CoT-VLA, Visual Chain of Thought Reasoning for Vision Language Action Models. Are you ready to get started?
Absolutely. This paper is a fascinating contribution to the field of robotics and AI. It introduces a new approach to vision language action models, or VLAs, by incorporating visual chain of thought reasoning. But before we get into the details, can you remind us what VLAs are?
Of course. VLAs are models that connect visual perception, language understanding, and robotic action. They take in images and natural language instructions and then output actions for a robot to perform. This integration allows robots to understand complex tasks described in human language and execute them in the real world.
That's right. And traditionally, these models have focused on direct input-output mappings. In other words, they take the input and immediately predict the action, without any explicit intermediate reasoning steps. But the authors of this paper argue that this approach has limitations, especially for complex manipulation tasks.
Exactly. The main limitation is the lack of temporal planning or reasoning. Without intermediate steps, the model can struggle with tasks that require multi-step reasoning or planning. That's where the concept of chain of thought, or CoT, comes in. Have you heard of CoT in the context of language models?
Yes, I have. In language models, chain of thought prompting encourages the model to think step by step, breaking down complex problems into sequential, explainable steps. This has been shown to improve reasoning capabilities in large language models. The exciting part of this paper is that it brings this idea into the visual and robotic domain.
That's a great summary. The authors propose a method where, instead of directly predicting actions, the model first generates a subgoal image. This image represents an intermediate state that the robot should reach. Then, the model predicts a sequence of actions to achieve this subgoal. This two-step process allows the model to think visually before acting.
That's a clever idea. By generating subgoal images, the model can leverage information from both robot demonstrations and actionless video data. This is important because there's a lot more video data available than annotated robot demonstrations. Using subgoal images as intermediate reasoning steps unlocks the potential of using abundant unlabeled video data to improve the model's visual reasoning capability.
Exactly. The system introduced in the paper is called CoT-VLA. It's a state-of-the-art 7B parameter model that can understand and generate both visual and action tokens. The authors show that CoT-VLA outperforms previous VLA models by 17% in real-world manipulation tasks and 6% in simulation benchmarks.
Impressive results. Let's talk about the architecture of CoT-VLA. The model is built on top of VLA-U, a unified multimodal foundation model. VLA-U can understand and generate text and images, making it a strong backbone for this kind of reasoning.
That's right. VLA-U uses a unified vision tower to encode visual inputs as discrete tokens, which are aligned with textual information. This enables the model to perform autoregressive image and video generation, as well as text generation. The visual features are processed through a projector and then passed to the language model backbone.
During training, the model is optimized for two main objectives: subgoal image generation and action sequence prediction. For subgoal image generation, the model uses causal attention, predicting future image frames autoregressively. For action prediction, it uses full attention, allowing all action tokens to interact with each other.
The hybrid attention mechanism is a key innovation here. Causal attention is used for generating images and text, while full attention is used for predicting all action dimensions at once. This combination improves the model's performance, especially in complex tasks.
Another important aspect is action chunking. Instead of predicting a single action at each time step, the model predicts a sequence of actions. This approach, inspired by recent advances in robot learning, helps the model plan over longer horizons and improves efficiency.
Let's discuss the training data. The model is pre-trained on a combination of robot demonstrations and actionless videos. Robot demonstrations include sequences of images, actions, and language instructions. Actionless videos include images and language descriptions, but no action annotations.
That's a smart way to leverage the abundance of video data available online. By training the visual reasoning step on both types of data, the model can learn from a much larger and more diverse dataset. The action generation step is trained only on robot demonstrations, since action labels are required.
The training process involves optimizing the LLM backbone, the projector, and the depth transformer, while keeping the vision tower fixed. The overall loss combines the visual and action prediction losses.
After pre-training, the model is fine-tuned on task-specific robot demonstration data for downstream deployment. This adaptation phase allows the model to specialize for new tasks and environments.
Now, let's talk about the experiments. The authors evaluate CoT-VLA on several benchmarks, including the Libero simulation benchmark, the Bridge V2 real robot platform, and the Franca tabletop real robot setup. These experiments test the model's ability to generalize across different tasks, environments, and embodiments. Goal INHI, or spin of recap.
In the Libero benchmark, CoT-VLA achieves the highest or second highest success rates across all task suites, outperforming strong baselines like diffusion policy, Octo, and OpenVLA. The model demonstrates strong capabilities in spatial reasoning, object manipulation, goal achievement, and long-horizon planning.
On the Bridge V2 platform, CoT-VLA is evaluated on tasks that test visual robustness, motion generalization, semantic generalization, and language grounding. The model achieves competitive or better results compared to baselines, showing its ability to handle diverse and challenging scenarios.
The Franca tabletop experiments are particularly interesting because they test the model's adaptation to novel real-world environments with limited demonstrations. CoT-VLA achieves the best average performance, especially in multi-instruction tasks that require complex language grounding.
The authors also conduct ablation studies to analyze the impact of different components. They show that action chunking, hybrid attention, and visual chain-of-thought reasoning all contribute to improved performance. Pre-training on both robot demonstrations and actionless videos leads to significant gains in downstream task adaptation.
One of the most insightful findings is that better visual reasoning directly translates to better action prediction. In an ablation study, using ground truth goal images instead of generated ones improves the success rate by 40% on challenging tasks. This suggests that advances in visual reasoning and goal image generation can lead to better robotic performance.
That's a crucial point. The quality of the intermediate subgoal images is directly linked to the model's ability to plan and execute actions effectively. As visual generation models improve, we can expect even better results from this approach.
Of course, the paper also discusses some limitations. Generating intermediate image tokens during inference introduces computational overhead, making the process slower than direct action generation. The visual quality of the generated images is also lower than state-of-the-art diffusion-based models.
The authors suggest that recent advances in fast image generation and large-scale multimodal models could help address these limitations. They also mention that action chunking can introduce discontinuities between action sequences, which could be mitigated with temporal smoothing techniques.
Another limitation is that, while CoT-VLA leverages actionless video data during pre-training, current computational constraints limit its ability to generalize visual reasoning to entirely new tasks. However, the authors are optimistic that advances in video and image generation, as well as world models, will enhance generalization capabilities in the future.
Let's take a moment to summarize the key contributions of this paper. First, the authors introduce visual chain-of-thought reasoning through subgoal image generation as an intermediate step for robotic control. This approach improves interpretability and performance.
Second, they develop CoT-VLA, a system that incorporates visual chain-of-thought reasoning and a hybrid attention mechanism. This system achieves state-of-the-art performance across multiple robot platforms and tasks.
Third, they demonstrate that leveraging actionless video data for pre-training enhances the model's visual reasoning capabilities, leading to better action prediction and generalization.
And finally, their comprehensive experiments and ablation studies provide strong evidence for the effectiveness of visual chain-of-thought reasoning in vision-language action models.
Before we wrap up, let's discuss some potential future directions. What do you think are the most promising areas for further research based on this work?
I think improving the speed and quality of image generation is a key area. Integrating faster image generation techniques or more efficient inference methods could make this approach more practical for real-time robotic applications.
I agree. Another area is enhancing the model's ability to generalize to entirely new tasks and environments. This could involve scaling up the pre-training data, incorporating more diverse video sources, or developing better world models.
There's also potential in combining visual chain-of-thought reasoning with other forms of intermediate representations, such as language descriptions, key points, or semantic maps. This could provide even richer reasoning capabilities.
Absolutely. The integration of multimodal reasoning, combining visual, linguistic, and spatial information, could lead to more robust and flexible robotic systems.
It's exciting to see how ideas from language modeling, like chain-of-thought prompting, are being adapted and extended to the visual and robotic domains. This cross-pollination of ideas is driving rapid progress in AI.
I couldn't agree more. The CoT-VLA paper is a great example of how interdisciplinary research can lead to innovative solutions for complex problems.
Before we finish, let's briefly touch on the implementation details. The model is trained on a mix of datasets, including OpenX embodiment for robot demonstrations and something-to-something and Epic Kitchen 100 for actionless videos. The training process is computationally intensive, requiring thousands of GPU hours.
The hyperparameters are carefully tuned with a large batch size, high-resolution images, and a significant number of epochs. Fine-tuning is performed for each downstream task to ensure optimal performance.
The authors also provide detailed information about the data weights and subgoal prediction horizons for each dataset. This level of transparency is helpful for researchers who want to reproduce or build upon this work.
In conclusion, CoT-VLA represents a significant step forward in vision-language action models. By incorporating visual chain-of-thought reasoning, the model achieves better interpretability, generalization, and performance in complex robotic tasks.
That's a great summary. If you're interested in learning more, the authors have made videos and supplementary materials available online. We encourage you to check them out for a deeper understanding.
Thank you for joining us for this in-depth review of CoT-VLA, Visual Chain-of-Thought Reasoning for Vision-Language Action Models. We hope you found this discussion informative and engaging.
We'll be back soon with more reviews of cutting-edge AI research. Until then, keep exploring, keep learning, and stay curious.
Goodbye, everyone.
Goodbye.
To summarize, this paper introduces CoT-VLA, a vision-language action model that incorporates visual chain-of-thought reasoning through subgoal image generation, achieving state-of-the-art performance and improved generalization in robotic manipulation tasks.